Okay, Assalamualaikum warahmatullahi wabarakatuh and good morning to all of you. So, so now is, for your information, now is week 11 already. And supposedly, chapter 5 we should cover, we should start last week in week 10. However, I had to start this chapter 5 in this week 11. So that's why please take note that over here in your slide, it stated that this is for week 10, but in the ULearn, if you want to see the video in the ULearn, please make sure that you refer to week 11. Okay. So basically today we will start with a new chapter, chapter 5. And this is actually the last chapter, the final chapter that is included in your final exam. Okay, so in your final exam, basically we will cover 5 chapters. Okay, chapter 1 until chapter 5. Okay, so so without wasting time, let's start with chapter 5. Okay, so I've divided the slide into three parts, and this is part 1. So part 1 we will cover on the introduction on bipolar junction transistor, or we usually call it as BJT. Okay, BJT transistor. So we will cover on the structure of BJT, basic operation of BJT, and also the characteristics and parameters of a BJT. Okay, so these are the learning outcomes for this chapter. So please make sure at the end of this chapter, you must be able to describe the basic structure of NPN and PNP transistor, describe the operation of BJT, discuss the basic BJT parameters and characteristics, and lastly, you must be able to analyze BJT circuits. Okay, so this is very important. Learning outcome for each chapter is very important to make sure that you understand, okay, the chapter. So now let's look at the first one. So over here shows the transistor structure. Okay, so before I go into the transistor structure, I would like to flash back on chapter 4. So chapter 4, you have learned on diode. Okay, so diode is an electronics equipment that consists of the N and also the P. Okay, we have the PN junction in diode. Okay, transistor is also another electronics equipment. But the difference between a diode and a transistor, if you look at here, for a diode, you only have N region and P region. And so you only have one PN junction. But in transistor, if you look at here, you have N region, P region, N region. So over here, you can see that you have two PN junction. So this is the first PN junction, this is the second PN junction. Same for this one, you have P region, N region, and P region. So you have the first PN junction and this second PN junction. Compared to diode in chapter 4, you only have something like this. Maybe you have the N region, this is P region. Okay, so you only have one PN junction. So that is the difference between a diode and also a transistor. Okay, so in transistor is constructed by 3 dope semiconductor. Okay, 3 dope semiconductor. So it has, I call this as feet. Okay, kaki transistor. In Malay, it is kaki transistor. Okay, so the first one we have the emitter. So this is the emitter. The second one, we have the base. And the third one, we have the collector. Okay, and separated by two p-n junctions. This is what I told you before. For the transistor, you have two p-n junction, one p-n junction, second p-n junction. Okay, first is the BC junction. Okay, separating the B and also the C. And the second one, we have the ones that separating the base with the emitter over here. Okay, so for a BJT transistor, okay, we have two types. So the first one is what we call as the NPN transistor. This one is the PNP transistor. The difference is here. Okay, so over here, the materials over here, you have the N region, P region, N region. This one for the PNP, this P region, N region, and P region. Okay, so this one, the P region in the middle, and this one is the N region in the middle. So just based on the name itself, NPN, this is PNP. Okay, so if you look at here, the P region is slightly doped and very thin compared to E and C region. So if you look at here, the B region over here, this is smaller compared to the C and also the E. Okay, so that is the structure of a transistor. And this is the symbol of a standard BJT. When I talk about BJT, BJT is actually, I mean transistor. Okay, so this is the standard symbol of a transistor. So the symbol for NPN transistor is different to the PNP transistor. Okay, the only difference is you can see based on the arrow over here. Okay, so for NPN transistor, the arrow here is not pointing in. Okay, not pointing in. It is pointing out. For the PNP, the arrow is pointing in. Okay, and this you must make sure that the arrow is always located at the emitter. This is the emitter. Okay, so you must be able to differentiate. For example, given a circuit, given a transistor symbol, you must be able to differentiate whether this is an NPN transistor or the PNP transistor based on the arrow. Okay, so these are examples of pictures of a transistor. So even though the structure of the transistor is different, but still it has the same function, which is as a transistor. So if you look at here, this is the transistor that we usually use. It looks like this. You have three feet, 1, 2, 3. Okay, because remember, transistor has the emitter, base, and collector. So all of this, even though the design is different, but you will always see that it has 3 feet. Okay, 1, 2, 3. This is 1, 2, 3. This is 1, 2, 3. Okay, the case itself also act as a feed, which is the collector. Okay, and this one we have 3. 1, 2, 3. Okay, so the ones that we usually use in FKA laboratory is this one and also this one. Okay, so if you look at here, this is the emitter, base, and this is the collector. So you must refer to the usually in for every equipment, electronic equipment, they will state which which fit is the emitter, base, and the collector. Okay, so for this one, this is emitter, this is the base, and this is the collector. This one, this is the base, this is the emitter, and this is the collector. Okay, and so on. So first now let's look at the first types of PJT transistor, which is the NPN transistor. So remember, NPN transistor, the arrow should pointing up. Okay, NPN transistor, the arrow should always pointing up. So if you refer to the figure, the symbol here, okay, you can see that the VBE is the voltage between the base and emitter. So that's why the name is BE. Okay, this is the base, this is emitter. So the VBE is the voltage between the base and emitter. So the base is over here, the emitter is over here. So by right, the VBE is here. It's between the base and also the emitter. Okay, so the base terminal is always positive with respect to emitter. Take note, the base of the emitter, that's why this is positive, so this is negative. Always positive with respect to the emitter. Another voltage is the VCE. So VCE is the voltage between the collector and also the emitter. So you have the VCE over here. Okay. So what is the function of VCE? VCE collector supply voltage with respect to the emitter. Okay. So for NPN transistor to conduct, the collector is always more positive with respect to both base and the emitter. Okay, so look at here, this is also very important. In order for the transistor to conduct, collector, this part over here is always more positive with respect to the base and the emitter. So that's why for the VCE over here, this is positive, this is negative. Okay, because the collector is always more positive. This one, if the same for this one, this will be positive, this will be negative. Okay, so the transistor is a current operated device. Okay, a large current IC. Okay, this IC we also call it as the collector current. IB is the base current. IE is the emitter current. Okay, so when I told you IC, so I mean is the collector current, the current at the collector. So a large current IC flows freely through the device between the collector and the emitter terminals when the transistor is switched fully on. However, this only happens when a small biasing current is flowing into the base terminal of the transistor, at the same time thus allowing the base to act as a sort of current control input. Okay, so over here, this is a formula. Beta equals to ICIB. Okay, so what is beta? In the next slide, I will explain to you what is beta. So over here, beta is collector current divided by the base current. Okay, so what is beta? DC current gain in an NPN transistor is the ratio of the collector current to base current, called the beta. Okay, so the beta here is actually the DC current gain. So if the question asks you to calculate for the DC current gain, what it means that it asks you to calculate the beta. And the formula is, okay, IC, beta is equal to IC over IB. Okay, this IC and IB are determined at the particular operating point on the characteristic. Okay, so this later you will understand when we do the examples. Okay, so this value beta can be large Okay, the value is between 50 to 400, mostly mid-range for practical transistor. Okay, so for example, if beta is 200, IC is 200 times the magnitude of IB. Why? Because you know that beta is equals to IC over IB. Okay, and you know that IC over IB beta is equals to 200. So IC is equals to 200 IB. Okay, so that's why stated over here, if the beta is 200, IC is 200 times the magnitude of IB. Okay, so this also explained in the previous slide, stated that the current IC is large compared to IB. Okay, so this makes the NPN transistor a useful amplifying device when used in its active region, as IB provides the input and IC provides the output. Okay, the beta has no units because it is a ratio. So current divided by current, there is no unit for beta. That one is NPN transistor. Now let's look at the PNP transistor. So PNP transistor, the difference is based on the arrow. So over here, so look at here. This figure and this figure is actually the same. It is a PNP transistor. The difference is that the way we draw the symbol. Okay, so this one, the emitter is at the bottom, collector at the top. However, for this one, we draw it, the emitter at the top and the collector at the bottom. Okay, so that's why the arrow is over here. Okay, so remember, if you have a circuit and given a circuit like this, usually we don't label the circuit. This is E, this is B, this is C. You should know by yourself. Okay, so how to know is based on the arrow. So since the arrow is over here, you should know that this is the emitter. And since the arrow is pointing in, then this is the PNP transistor. Okay, so very simple. So PNP transistor has very similar characteristics to NPN, except that the polarities or the biasing of the current and voltage directions are reversed for any one of the possible three configurations. Okay, so the VBE here, now the VBE here, the VBE is now negative at the base, and positive at the emitter. Okay, reverse from the PNP. If you look at here, for the PNP, for the VBE, the base is positive. This one is negative. But for PNP, the base is negative. Okay. So the base terminal is always biased negative with respect to the emitter. Okay. The base will always bias negative. This one, the base NPN, the base is always positive. So the VCE is emitter supply voltage with respect to the collector. So for PNP transistor conduct, the emitter is always more positive with respect to both the base and the collector. So if you look at here, the arrow here is actually shows you the direction of the current. Okay, so for the NPN, the previous NPN, the arrow is like this, so the current actually flows like this. So the emitter, the current goes up. But for this one, since the arrow is pointing in, so the current is like this. Okay, current is like this. So for PNP, the emitter is always more positive with respect to both base and collector. This one, the capacitor is always more positive. So now let's look at the basic transistor operation, how this transistor actually works. Okay, so the two PN junctions, the BC and the BE, must be correctly biased with external DC voltage to operate properly as an amplifier. Okay, so notice that in both cases, BC is reverse bias, BE is forward bias. Okay, so look at here, this is the circuit with the NPN transistor. This is a circuit with the NPNP transistor. So if you look at here, the BC, this is the BC. BC is reverse bias, BE is forward bias. Same for the PNP, BC is reverse bias, BE is always forward bias. Okay. So now let's look at, this is the transistor current. This is your transistor and this is the symbol. Okay, so this is NPN. So NPN, the arrow is pointing out. So this, the current flow is like this. While for the PNP, the current flow is from the ammeter and out to the collector. Okay, and remember BC is always reverse bias, BE is always forward bias. Okay, and from this you can know that IE is equals to IC plus IB. IE is equals to IC plus IB. Same for this one, IE is equals to IC plus IB. Okay, and take note that IB is very, very small compared to IC and IE. Okay, so this is some questions that I think you can answer based on the previous slide. Okay, so make sure that you're able to answer these questions. So now let's look at, let's go to the transistor characteristics and parameters. So for the characteristics and parameters, we will cover on the DC beta, which is the beta DC, and also DC alpha, alpha DC. Configurations and current and voltage analysis, collector characteristic curves, and we also will look at into what is cut-off region, saturation region, and DC load line. So BJT transistor is actually a current control device. Okay, so the values of the collector and emitter currents are determined primarily by the value of the base current. Okay, so for example, you have this circuit. This is you have this base circuit, and you have the beta equals to 100. So the small increase in the base current, okay, produces a large increase in IC and IE. So that's why it's stated over here, the values of the collector and emitter currents are determined based on the value of the base current. Why? So look at here, this is the base current 10 micro, this is base current 20 micro. Okay, the small increase in the base current from 10 micro to 20 micro, it will produce large increase in IC and also IE. So if you look at here, for IB equals to 10 micro, this will become 2 milli, this 2 milli. For 20 micro, this become 4 milli, and this is 4 milli. Okay. So now let's look at the DC beta and also DC alpha. So basically DC beta already introduced in the previous slide. So you know that beta DC is equals to IC over IB. But for alpha, alpha is IC over IE. Okay, so don't get confused. Make sure that the formula that you use is correct. Beta is IC over IB, alpha is IC over IE. So beta DC range from less than 220 to 200 or higher, while alpha is range from the 0.95 to 0.99 or greater. So example 1. Given a certain transistor has a beta DC of 200, when the base current, this is beta DC 200, when the base current, okay, base current is IB, is 50 microamp, determine the collector current. So determine IC. Okay, so by using this formula, beta equals to IC over IB, you can find IC. Okay, just put in the values, you will get the collector current equals to 0.01 ampere. Okay, next is, this is a table to show you that different configuration will result in different circuit parameter. Okay, so basically for a BJT, we have 3 configurations, okay, that we will learn further in the next slide. Okay, so we have 3 transistor configuration. The first one is what we call as the common emitter. The first one is what we call as the common emitter. The second one is the common collector. And the third one is the common base. Okay, what is the difference? Okay, based on the circuit, I will explain in the next slide. Okay, so you just look at here. For the common emitter, you can see the difference of the, for example, this is the voltage gain. Okay, so if the transistor configuration is common emitter, so you should expect that the voltage gain is high. If it is a common collector, it is less than unity, but it is common base, it is high, same as the CE. Okay. Okay, I think this is not that important, but you can always refer here if you want to know the difference of circuit parameter for a different configuration. Okay. So now let's look at the first configuration. This is common base. How do we know that it is a common base? Because the ground here is connected to the base. Remember, this is the base. This is the base. This is, you have the arrow, so meaning this is the emitter and this is the collector. So if the ground is connected to the base, then it is common base. If it's connected to the emitter, then it is common emitter. But if it is connected to the collector, then it is the common collector. Okay. So now let's look at how this common base works. So the arrow, you refer to the figure here, the arrow in the graphic symbol defines the direction of emitter current. Okay, defines the direction of the emitter current, because this one is PNP. Look at here, this is the PNP. So you know that the PNP, the arrow of the emitter is like this. So you should know that the current direction is like this. But for the NPN, the arrow here is like this, so the current direction is to the left. Okay, so the arrow in the graphic symbol defines the direction of emitter current through the device. Okay, so remember, current flows from positive to negative. So this is positive, this is negative, this is positive, and this is negative. Okay, so over here, You know that IE is equals to IC plus IB. The emitter-based junction is forward bias, while collector-based junction is reverse bias. Okay, so the base is common to both the input and output side of the configuration. So to fully describe the behavior of three-terminal device, such as the BJT, requires two set of characteristics. Okay, so remember in chapter 4 for the diode, you have the VI characteristic in the graph, the diode VI characteristics. You only have one graph, okay? Because diode only has two terminals. But this one, for the transistor, you have a three terminal. So to describe the operation, the characteristic of a BJT transistor, you need two sets of characteristics. You cannot have only one VI graph, okay? You need to have two. So the first one is the driving point or the input characteristic. So this is what we call as the input characteristic. And the second one is the output or collector characteristic. So this is the output or collector characteristic. So you need to have two graphs. Okay, so now this is the input characteristics. So it plots the emitter current with respect to the VBE. Okay, so VBE is the input voltage. Okay, so this graph actually shows you various output voltage. So when VCB is 20, VCB equals to 10, and VCB equals to 1 volt. While for the output or the collector characteristics, so here it plots the IC with respect to the VCB. Okay, remember, emitter is the input, collector is the output. Okay, and you have for various input current, okay, 7 milli, 6 milli, and so on. Input current is IE, okay, because emitter is the input. So this is an exercise using input and output characteristic. So look at here, you were given two graphs. This is the input graph, this is the output graph. Okay, using the output characteristic, determine the resulting collector current if emitter current is 3 milli and the VCB is equals to 10 volt. Okay, so the question asks you the resulting collector current. Find, okay, collector current, find IC. So based on this graph, the VCB is 10 over here, IE is 3 milli. So it should be somewhere here. So IC is 3 milli. Second question, using the output characteristics, okay, this output characteristic, determine the resulting collector current if emitter current remains at 3 milli but the VCB is reduced to 2 volt. Okay, so if you look at here, still the emitter current is 3 milli but the VCB is reduced to 3 volt, 2 volt. So 2 volt should be somewhere around here. Okay, so the value is still the same. It is at 3 milliamp. Number 3, using the input and output characteristic, determine VBE if IC is 4 milliamp and VCB is 20 volt. Okay, so yeah, I think this one you can do it by yourself. It's very simple. You should get the answer equals to 0.74 volt. Okay, so please do this question. Using both graph, determine VBE. If IC and is 4 milliamp, VCB is 20 volt. You should get it is equals to 0.74 volt. Okay. Okay. Let me just share with you the answer. This one is IC, it's 4 milli. So this IC 4 milli, VCB is 20. So your IE should be 4 milli. Okay, so go to the input graph. This is 4 milli. Okay, 4 milli. And the VCB is 20. You should refer to this line. Okay, so this is roughly, the answer should be around here, 0.74 volt. Okay. Okay, so over here, this is analysis based on common base configuration. So for example, look at here, you have this circuit. This is the common base because the base is connected to the ground. Okay, so from this figure, actually, for the circuit analysis for transistor, you will use a lot of KVL. Okay, Kirchhoff voltage law. So Kirchhoff voltage law you already learned in chapter 2. So I really hope that you already somewhat expert on KVL already. Okay. So I will not show you the step-by-steps on the KVL. Okay, you should know how to do the KVL. So for example, this is the first loop here. So if you do a KVL over here, you can do a KVL over here. Okay, so if you do KVL over here, you will get negative VEE plus IERE plus VBE is equals to 0. And you can get IE is equals to VEE minus VBE divided by RE. Okay, this one, if you do a KVL for this loop, this big loop over here, you will get negative VEE plus IERE plus VCE plus ICRC minus VCC. Okay, equals to 0. Okay, so VCE is equals to VEE plus VCC minus IERE minus ICRC. Okay, so remember, usually we assume that IE is the same as IC because we assume that the base current is very, very small. Okay, so when you know that IE is equals to IC plus, you know that IE is equals to IC plus IB. Okay, but usually we assume that IB is very, very small. So usually we assume that IE is equals to IC. Okay, so when you assume IC equals to IE, so you will get VCB equals to VCC minus ICRC. Okay, so this one is the loop here. This is the first loop. Based on the first loop, this is based on the big loop here. This is based on the second loop here. Okay, all of this is KVL. So now let's look at example 4.17. Given the circuit, and also you have the beta value here, beta equals to 60. determine the voltage VCB and the current IB for the common base configuration of figure 4.43. Okay, so first, this one, actually the step is already shown in the previous slide. This is from the previous slide, okay? But so this one, the first step is applying Kirchhoff voltage law to the input circuit. Okay, this is the input. This is the V in, this is the out. Okay, this is the ammeter, this is the collector, this is the base. Okay, applying Kirchhoff voltage law to the input circuit, over here, you will get negative VEE plus IERE plus VBE. So IE is equals to VEE minus VBE over RE. So already explained in the previous slide. So by substituting values, we obtain IE. So VEE is 4. VBE is, okay, look at here, VBE is over here. Usually VBE, we use equals to 0.7 volt. Okay, so take note that VBE is equals to 0.7 volt. Okay, and RE is 1.2 kilo ohm. So IE is equals to 2.75 milliampere. So next, applying Kirchhoff voltage law to the output circuit. Okay, this is the output circuit. So you will get negative VCB. Negative VCB is over here. Negative VCB plus ICRC minus VCC is equals to 0. So when you assume IC is equals to, this one you will get VCB equals to VCC minus ICRC, and you assume IC equals to IE. Okay, so VCC is 10 volt, IC is equals to IE. So IE is 2.75 milliampere, RC is 2.4 kilo ohm, so you will get VCB equals to 3.4 volt. And the last one you want to calculate for the base current, so use this formula. IB equals to IC over beta, you will get 45.8 microampere. Okay. So that one is common base. This is common emitter. Okay, so this is common emitter. So look at here. The emitter, this is the emitter. So emitter is connected to the ground. Emitter is connected to the ground. So the emitter is common to both the input and output terminals, base and collector terminals. So same over here, it shows you two graphs. This is the input characteristics. This is the output characteristics. Okay, input characteristic IB respect to VBE. Output is IC respect to VCE. Okay, take note that since this is common emitter, and now the emitter is the common base emitter. In the previous slide, the base is common to both the input and output. Okay, so for common base, is one that we already learned before. Common base, IE is the input, IC is the output, IB is the common. But for this one, this is the input, yeah. Now, the common, for common emitter, IE is the common. Now the input is IB. IB is the input and IC is the output. Okay, so look at it. That's why the graph here, input is IB respect to VBE, output IC respect to VCE. Okay. So this one is just to show you that this is the current flow for a common emitter. Okay, this is the emitter, collector base. The current flows like this. Okay, this is the VCE, this is VCB, VBE. This one, this is the transistor characteristics. So you look at here, the figure here, this is the collector characteristic curve. Okay, collector. This is IC with respect to VCE. Collector characteristic curve. So it shows a graphical illustration of the relationship of collector current and VCE with specified amount of base current. So the first region, okay, remember, look at here, this is the characteristic of a transistor. You have three regions. So the first region here is what we call as the saturation region. In the middle, we have the active region. The third one over here, we have the breakdown region. Okay, similar to diode. Okay, so as VCE is increased, IC increases until B. Then it flattens. So look at here, from B to C, the graph flattens, which is this is the active region. So the current remains about the same in the linear region from 0.7 volt to the breakdown voltage. So you look at here, this is 0.7 volt. Okay, so that's why the current remains about the same in the linear region from 0.7 volt to the breakdown region. So that's why for just now, for the example, for the transistor the transistor, the ones we use 0.7 depending on the transistor configuration. Okay, and the last slide over here, this is the same collector characteristic curve. This is a saturation region, this is active region, and this is the cutoff region, a breakdown region. Okay, for different base current. Okay, so this is the end of the first part for chapter 5. Okay, so I hope that you understand. This is the basic concept of transistor, BJT transistor. So if you have any questions, feel free to WhatsApp me or PM me through the Telegram group personally or in the subject group. Okay, so and we will continue with the part 2. Okay, so we will continue with part 2 in the next video. However, I will put this video okay, for part 2 in the same week, which is week 11. Okay, so in week 11, we will cover part 1 and also part 2. Okay, so we will end our video for this part 1 and continue with part 2 in the next video. Okay, so thank you very much.